Good morning, afternoon, or evening. My name is Josh, and I will be your instructor. We're going to talk about parallel resistive circuits. The whole goal is to help you better understand how we're going to do the math on these parallel resistive circuits so that out in industry you can be able to calculate what is going to be the volt drop, what is going to be the resistance, what is going to be the current through each one of these parallel branches that you can be able to indeed apply out in the field. This outcome, once again, analyze this circuit so that you can be able to understand these relationships. This is what we're going to get into a little bit more depth, and the way that we'll do it is with some of these other desired outcomes here. Our objective, indeed, define a parallel circuit. What the heck is this thing? Calculate total resistance, calculate resistance of each branch, calculate the total current, calculate the current of each branch, even state and apply Kirchhoff's current law, describe the effects if we open up one of those branches, what happens to the rest of the circuit, what happens to total voltage, what happens to total current, and then use the current divider rule. That's tangential at the very end for you to be able to understand just one more way, one more math way of being able to do these circuits. So what are parallel circuits? Indeed, they are circuits that have more than one path for current to flow. That's key, folks, that's key. So make sure that you understand when you're looking at this diagram here, we're coming out of the panel with our black, our white, and our green. And so we can see that there are nodes or junction points that go from that line coming off the panel to each one of these receptacles, okay? And those are separate branches. That's what we will call those, all right? And this is a parallel circuit. What happens to the voltage in these parallel circuits? Well, if you remember series and what happens to voltage there, we're gonna put an example up here so that you can figure this out. If we look and we have a 120 volt light bulb, and we've got 4 of them, and each one of those bulbs are 100 watts, then if we connect them in series, what's going to happen to that voltage? Are they going to see that full 120 volts? So we get our 400 watts is our total power. We take our total power and divide that by our total or applied voltage, okay, and we get our total current. Now remember, in series, that current, that total current is going to equal the current through each one of those loads, okay? So our voltage of, for example, bulb 1 is going to equal the power of bulb 1 divided by that current, all right? Which will be 100 watts divided by 3.3. And check it out, 30 volts. That thing is going to be dim. That's going to suck. So this is why when we're hooking up light bulbs, we really want them to be in parallel, because with our voltage laws, that voltage in a parallel circuit is going to remain virtually the same across each one of those branches. So yeah, it's a big old thumbs down. Here's our parallel example. If I have 120 volts, and it's going to be applied across the resistor, then that resistor is going to see that full 120 volts if we don't count the resistance across the line itself, okay? So it'll see that full 120 on branch 1, and it'll see that full 120 on branch 2. Sorry, my face is probably in the way of branch 2 there. But that's the cool thing about voltage in a parallel circuit. Now let's get to resistance. When we're adding resistance in a series circuit, the more resistors we add, the larger our resistive value, our total resistance, right? But in parallel circuits, that's not the case. The more resistors that we add, in fact, that is less, or that lessens our total resistance. Because as our current draw increases, right, our total resistive value decreases. Okay, because our voltage is remaining constant. So this is the relationship that you're going to see, and we're going to talk about inversely proportional relationships in a little bit, but that's what we've got here in a series circuit. Our resistance is additive or directly proportional, and in parallel circuits, it's inversely proportional. We've got a couple of methods that we can use to find total resistance. So this is our total resistance formula at the top, where we've got our RT is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, or the reciprocal method, which is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And in essence, these two are the same thing, okay? Because once you do the cross multiplication of method 2, you will come up with the formula in method 1. Let's go through an example here. If I've got two resistors in parallel, each resistor has 40 ohms. Let's solve for the total resistance. This is what our little diagram would look like. Just going to remove my face so that you can actually see what's going on here. So we've got 40 ohms on resistor 1 and 40 ohms on resistor 2. If we use that total resistance method, then we will go, our total resistance is going to equal to 1 over R1 plus 1 over R2, which is 1 over 40 and 1 over 40, as you can see there. And this is, if we do that 1 over 40, we'll get 0.025. We'll add those two together. 0.05. 1 over 0.05 is going to equal 20 ohms. And what I want you to recognize is that 20 is smaller, in fact by half, of 40. Okay? And that's key. Your total resistance in a parallel circuit will always be less than any single resistive value in that circuit. So that's an easy check, right? If you're pulling out a total resistance of 60, you probably did the math wrong. So it's a really quick way, really easy way to check that you've done that question correctly. When looking at your calculator, what you really want to look for is that second function button. Okay, so you're going to use the second function, and then you're looking for the x to the -1. If you look at that number 2, just above that number 2 in that orange color, you'll see x to the -1. That's how you're going to be throwing in those numbers in your calculator using the inverse function on your calculator. Okay, just a note of where it is. On that particular version, the EL520X, it's above the 2. On the Sharp EL531 XT, it is above the x squared. So if we were to put this in our calculator, we would go 5 second function x1 plus 10 second function x1 plus 15 second function x1 equals, and then you would, whatever that answer is, you would second function to the x1, that answer, and that will actually give you your total resistance. And that's how you would use the calculator to figure that out. Why writing things down matters for retention. Okay, I throw this in there just to make sure that when you are doing these questions, please, please, please write the progress down, because not only will it help you retain the process of how to do it properly, but you'll be able to see your mistakes really quickly. And with all my students, as I go through this process with them, and if they've made a mistake, I can easily see it along the way and just be like, you know what, there it is. Just grab that mistake, pull it out of there, and here's how you fix that. Also, as you write those things down, it's using another mechanism of your body to help you remember that process. So please write those things down. It does indeed help for retention. All right, now let's get into Kirchhoff's current law. The Kirchhoff's current law states that the algebraic sum of currents entering and leaving a junction point in a closed circuit is 0. In other words, the amount of current entering a junction must be equal to the current leaving that junction. How does that look? Well, if we look at the diagram here, we've got our I total is 10. All right, so that's leaving our source, and then we get to our node, which is located right underneath that I2. And you can see that the current therefore splits or leaves that junction, and 4 amps is being drawn to the final resistor, where 6 amps is being drawn to the first resistor. All right. So the amount of current that's entering that node, i.e. 10 amps, is equal to the current that leaves that node, i.e. 4 plus 6. Okay? You can see it going there. And if you note that at the bottom of this animation, those two values of 4 and 6 come back together to another node or junction, and then we can get our I total back to 10. Branch circuits, this is what we're talking about when we're talking about parallel circuits, and each branch will allow a certain amount of current to flow depending on the draw, okay, or how much resistance that branch has. And that's what we're talking about when we talk about draw, okay? Ohm's law, so key, folks, to understanding the math behind this, because Ohm's law can determine the current in each branch if we're given the other two values, right? Just like we did in the example with that series circuit previously, we're using a little bit of Ohm's law, we're using a little bit of the power formula to complete those calculations. So do be aware that Ohm's law, is our voltage being equal to our current multiplied by our resistance. And we'll get into that in just a minute. Also, the total current in a circuit that the circuit has to supply is the mathematical sum of those branch circuits. And that's what that diagram was showing us previously. So here's just a summative slide of kind of some things that we've gone through, some points to remember. So here we have another example, just a quick demonstration of what happens when the current at 15 amps is split and then it comes back together, current leaving a node and entering a node. So let's get into some examples. We've got 3 loads connected in parallel. Woo! Load 1 draws 5 amps, load 2 draws 6 amps, and load 3 draws 2 amps. What is the total circuit current? So if we're going to draw this one out real quick, I'll just draw it up here. Woo! We got a resistor in parallel, 1, 2, and 3. Let's all understand this is not art class right now. So we got 5 amps going through this first guy, 6 amps going through the second, and 2 going through the third. At this point, because we have a node right there, we will have 8 amps. Okay? And because we have our node right here, our total circuit current is going to be 13 amps, or in other words, 8 plus 5. You can also write our I total is equal to I1 plus I2 plus I3. Okay? So that's example 1. Example 2. A circuit consists of 2 resistors connected in parallel. Let's draw this bad boy out again. 2 resistors in parallel and the total is 12 amps. Okay? Then we get our lovely little note, and it's saying that one of the resistors has 4 amps flowing through it. And for this question, it doesn't matter which one. 4 amps goes there. So what is the remainder flowing through that last branch? Well, if we go back to this formula and look at it, we know that we just have I1 and I2 and I total. So we can say we know our I total is 12. And our I total is going to be equal to 4 plus I2. We don't know I2. So if we minus 4 from this side, get rid of that, minus 4 from this side. So 12 minus 4 is going to be equal to 8. Make sure you write amps on there. You might think of chickens if you don't label properly. So 8 amps is going to be our I2. All right? The current branches off here. So once again, another example. If we've got branch 1 and we're trying to find the current through that branch, we know that the voltage is 120 and the resistance is 10. All right? So we're going to use Ohm's law. V equals to I times R. And we'll rework this formula to solve for I. Okay? So we divide by R, divide by R. So V divided by R is equal to I. That's what we're using to solve for current. And as we do this, we see that the current becomes, or is, 12 amps. And we can do the same thing for the second branch, where we take 120 volts divided by 30, and we have a current of 4 amps. So if I were to ask you what is the total current then, you would use our I total is equal to I1 plus I2 and come up with 16 amps. When we open or close the branches, this is going to change some of those properties. So if you were given this diagram and we have our I total of 10 amps, our I1 is equal to 4, our I2 is equal to 6, and you can see the respective ohmic values or resistances. What if I opened that circuit, right? What if I opened branch 2, okay? Note how the current dropped from 10 amps to 4 amps. So I total is now equal to I1 because there's only one other branch. So just be aware that if I am opening and closing branches of a parallel circuit, that I will affect my total current. Okay? I didn't affect the voltage across branch 1. This voltage is still 120. That didn't change. The current in branch 1 also didn't change. Resistance also didn't change. The thing that changed was this value, our total current. Okay? So the current in branch 1, once again, these are just summative notes, will not change if branch 2 drops to 0 due to the switch being. When we're looking at this diagram, we can see we've got some more branches now, and we'll just look at the relationship of opening each branch. So see how I open branch 1. The current in branch 1 is now 0, and our total current decreased. Okay? If I open up branch 2, the total current going through branch 2 has now decreased to 0, and our total current overall has also decreased. So they are directly proportional. And that's the big takeaway from that diagram. This is once again that picture from the beginning. Sorry about the black background. Takes away the black wire. But we can see that we're just going to be plugging things in, and this can be like opening or closing those switches. So when you are wiring these things, you have to account each one of those receptacles as being 1 amp, so that it can indeed have that protective value on the circuit breaker of 12 amps for a 15 amp breaker. So yeah, you'll just plug those things in. It's kind of like opening and closing switches, but at no point will you have a current draw of greater than 12 amps, because if you do, then the breaker will trip. All right, so that's how you account for that. So now we're going to talk about, just real quick, about inverse proportions. I've alluded to them earlier, but the principle is that when one quantity increases, the other quantity decreases. Okay, that's this relationship. And the example that I like to use is, hopefully, the amount of time that a crew takes to accomplish a job decreases when the number of people in the crew increases. I know that some of you might be laughing because you know this might not always be the case, but in principle, that's what we're hoping for. And so this would be an inverse proportion. And there's been examples previously on inverse proportions. And so here, once again, is just that main principle. Now we're going to talk about the current divider rule. The current divider principle is for parallel circuits, and we can recognize here that in series circuits, they are voltage dividers, and in parallel circuits, they are current dividers. More specifically, when I am looking for the individual value of a current in a branch, or IN, that's going to be equal to the total current multiplied by this ratio of the total resistance divided by the resistance in that particular branch. And you can choose to use this solving for those questions that we did previously with current and finding the branch current values if you want to. Personally, I don't use this one often. I tend to focus on Ohm's law and the power formula for solving all of those values. But here it is for you. This slide here is some examples for you to fill in the blanks. You can pause and look and see if you can fill in those blanks. Here's another one where you can fill in the blanks and see if you can answer those questions. Once again, test, retest, folks. It's a great thing for memory retention. And that's it. I hope you enjoyed this lecture. If you have any questions, you can put them in the chat or in the comments, and that would be lovely. Have a great day, folks.